Hello everyone, I am Shetye and I would like to discuss with you all today some issues that I discovered about S-type stars while I was analyzing them. Before we proceed to the issues, let me give you a quick introduction on what the S-stars are. S-type stars are late-type giants with zirconium oxide bands and titanium oxide bands as their most distinctive characteristic feature. Apart from that, they all show enhancements of S-process enrichment, so heavy element production basically. However, they all don't make these S-process elements themselves because the S-stars come in two flavors, the intrinsic and the extrinsic, where the intrinsic ones are genuine thermally pulsing AGB stars, and the extrinsic S-stars, they owe their heavy element production, they owe their S-process enrichment to a binary interaction with a former AGB companion. So the intrinsic S-stars or the genuine thermally pulsing AGB stars, they are definitely very interesting to us because we can understand the AGB nucleosynthesis and we can understand the third dredge of physics and many more things. In fact, in the current context, the intrinsic S-stars are very interesting to us because they can help us understand the gaps in between AGB observations and AGB predictions or AGB models. So they are going to be the main heroes of my talk. To understand these S-type stars, I developed a tool which makes use of the high resolution spectra and also the Gaia parallaxes to disentangle their parameter space. And once we have an accurate set of stellar parameters for these stars, we can use this to perform their abundance analysis and to derive the heavy element abundances of these S-stars. So after a lot of careful work and also with the use of this routine, which we have recently developed, we performed such an analysis for a large sample of S-type stars, and we found many interesting things about the AGB nucleosynthesis, which you can find in the following papers. Now, one such thing which I want to address to you all today is as follows. So here I am comparing, I'm not comparing anything yet. Here you just have a figure of how the nucleosynthesis prediction evolves for zirconium abundance, for lanthanum abundance, and for the carbon over oxygen ratio. So what you see is how these abundances, the S-process element abundances and the carbon over oxygen ratio, it evolves as the star evolves along the AGB. Because as the star evolves along the AGB, we expect it to be more and more enriched with the S-process elements and also with the carbon over oxygen ratio to eventually become a carbon star. So this is just the pulse by pulse enrichment with these elements as per predicted by the AGB models. On top of it, now I will add the measured or the derived S-process abundances, which I found from my analysis. So which are marked with these dashed line here for zirconium and lanthanum, and the carbon over oxygen ratio is here. Now, at one time, if we want to compare these derived carbon over oxygen ratio and also the S-process elements with the predictions, we will need two different pulse numbers to justify the kind of enrichment we derive using spectroscopy. So what we can conclude from this is that the predicted carbon over oxygen ratios, they are increasing way too rapidly compared to the S-process abundances. Now, another way to see this would be using the huge sample of S-type stars, not only just the S-stars, but also carbon stars, which we have put here, technetium-rich carbon stars and S-stars. All the measured abundances here are compared with the AGB nucleosynthesis predictions. Now, if we were to live in an ideal world, and if everything was working as per our models think they do, then the S-type stars would be located in this zone, basically. Because beyond this zone, the star has a higher carbon over oxygen ratio, and beyond this zone, the star becomes a carbon star, so wouldn't be classified as an S-type star anymore. However, we find many S-stars which are located outside this zone. So they have a relatively high S-process abundance compared to their low carbon over oxygen ratios. So they even have a higher S-process enrichment than the carbon stars and a relatively low carbon over oxygen ratio. So that's how they diverge from what we predict, from the trend that we predict from the AGB models. And that this is something we have to understand because this hints towards a big gap in our predictions and our observations for such crucial parameter like the carbon over oxygen ratio. So more observational constraints can help us understand really what is lacking in our AGB models to constrain such problems then. Thank you so much.